In the realm of fluid dynamics, high-order methods such as flux reconstruction, FR, and discontinuous Galerkin, DG, have garnered significant attention due to their enhanced accuracy and reduced dissipation, dispersion errors at low to medium wave numbers. However, a major challenge associated with these methods is the necessity for high-order curved grids near body-fitted boundaries, which can complicate the process of generating the mesh. To simplify this process, the immersed boundary method, IBM, has been proposed, allowing for the avoidance of body-fitted meshes while accurately resolving complex flows using simple grids. Combinations of high-order methods and IBM have been developed to merge the numerical advantages of high-order methods with ease for mesh generation. For instance, Fidkowski and Darmofel, as well as M. Diaresis Uller et al., applied the cut cell method to simulate steady compressible flows based on discontinuous Galerkin. In contrast, recent work has demonstrated that IBM based on volume penalization, VP, is a robust and easy-to-implement method for high-order discretizations, such as FR or DG. Through eigensolution analyses, the error characteristics of this approach were clarified, showing that the penalization imposes the boundary condition by adding additional dissipation inside the solid. These studies have motivated the development of a combined volume penalization, selective frequency damping, SFD, approach for immersed boundary methods, particularly in the context of moving geometries. The proposed approach combines the volume penalization technique with selective frequency damping to improve the stability and accuracy of immersed boundary methods for moving geometries. The volume penalization method is used to enforce the no-slip boundary condition at the solid wall, while the selective frequency damping technique is employed to reduce spurious oscillations and improve the stability of the numerical solution. The combined approach is tested on various benchmark problems, including the flow past a cylinder and the flow in a lid-driven cavity, demonstrating its effectiveness in resolving complex flows with moving geometries. The research paper by Jiaqing Co. et al. Presents an extension of an alternative IBM treatment that combines volume penalization, VP, and selective frequency damping, SFD, for moving geometries. This extension involves reformulating the SFD formulation for moving boundaries, generating new manufactured solutions for numerical convergence testing, and validating the Navier-Stokes equations. The VP plus SFD approach offers additional damping inside the solid, enhancing the overall accuracy of the scheme. The methodology involves volume penalization, which imposes boundary conditions by introducing penalizing source terms inside the solid. The SFD method is used to compute unstable steady solutions by damping unstable modes. The paper focuses on the decomposition of the numerical solution into moving and oscillatory parts, with the latter requiring damping. In this refined version, we delve into the technical details of the VP plus SFD approach, its application in moving geometries, and its validation through the Navier-Stokes equations. The paper's findings highlight the importance of reformulating SFD for moving boundaries and the generation of new manufactured solutions for numerical convergence testing. The proposed immersed boundary method, IBM, for fluid structure interaction problems integrates a novel combination of the volume penalization, VP, and the selective frequency damping, SFD, techniques. This approach enforces the no-slip boundary condition by introducing a penalization term into the Navier-Stokes equations, while suppressing spurious oscillations through the SFD technique. The SFD formulation can be reformulated as a system of ordinary differential equations, driving the solution towards the target low-pass filtered solution. The implementation of this approach in a Navier-Stokes flow solver requires minimal computational overhead and uses two splitting schemes for the VP and SFD. Guidelines for selecting key parameters, such as the penalization parameter, control parameter, and filter width, are provided based on eigensolution analyses. The VP and SFD are only applied inside the geometry to mimic solid boundaries, with no treatment applied to the fluid region. To validate the proposed method, two test cases are presented. The first test case demonstrates numerical convergence using the method of manufactured solutions, a unidimensional advection diffusion problem with a moving boundary. The second test case showcases the validity of the approach for moving objects. In both cases, the finite difference, FR, method is used for spatial discretization. The results show that the proposed IBM effectively captures the behavior of fluid-structure interactions and achieves desired convergence rates. The paper presents a numerical solution to the unidimensional advection diffusion equation with a moving boundary, utilizing the immersed boundary method. It introduces a moving cylinder as a physical domain, where the right interface oscillates in time. An analytical solution and a flow domain are designed with user-defined parameters. To determine the source term, the method of manufactured solution is employed, allowing for the calculation of numerical error by comparing the residual against zero. The paper also formulates the modified equation for the moving geometry, incorporating the velocity potential term and the source term. Figures 3 and 4 illustrate the evolution of velocities at probe points, demonstrating the accuracy of the numerical scheme. The authors test the accuracy by setting the penalized solution equal to the analytical solution, varying in space and time to mimic the moving geometry. This innovative approach provides a robust and efficient way to solve complex fluid dynamics problems involving moving boundaries. The authors validate the combined volume penalization (VP) and shifted flux distribution (SFD) method for simulating moving boundaries in fluid structure interaction problems through two numerical test cases. In the first case, a moving solid element is placed in a rectangular domain, with the penalization parameter set to the time step and the SFD control coefficient set to a large value. The L2 norm error is computed for different polynomial orders and numbers of elements, demonstrating high-order convergence of the VP plus SFD method. The second case involves unsteady flow past a moving circular cylinder at a Reynolds number of 100, where the cylinder is free to move in the transverse direction. The background mesh is a rectangular computational domain, refined near the cylinder boundary to capture the periodic vortex shedding. A sinusoidal motion is imposed on the cylinder, with the frequency of the harmonic motion set to 0.9 times the vortex shedding frequency of a static cylinder. The simulation is run until the periodic vortex shedding fully develops, and the results show that the vortex shedding frequency locks onto the frequency of the forced oscillation, consistent with literature findings. The authors compare the performance of the standard VP method and the combined VP plus SFD method for two polynomial orders, p equals 2 and p equals 3, at two probe locations inside the solid element. The error in the lift coefficient is computed, and the Fourier spectrum is analyzed to highlight the vortex shedding frequency. The results demonstrate the accuracy and robustness of the combined VP plus SFD method in capturing the complex flow behavior around moving boundaries. The immersed boundary method is extended by combining volume penalization and selective frequency damping for moving geometries. The numerical solution inside the solid is decomposed into a predefined movement and an oscillatory part, where the latter is damped by the SFD approach. This method is tested with two cases: a manufactured solution problem to demonstrate high-order accuracy and the simulation of laminar flow past a moving cylinder for validation. The combined method shows improved accuracy in both cases. Immersed boundary methods have emerged as a crucial tool for numerical simulation of confined fluid and plasma turbulence in complex geometries. The significance of these methods lies in their ability to accurately model complex systems, as highlighted by K. Schneider's work. In the context of confined turbulence, traditional numerical methods often struggle to capture the intricate dynamics at fluid-solid interfaces. Immersed boundary methods, on the other hand, enable the simulation of complex geometries by introducing a virtual boundary within the fluid domain. The key advantage of immersed boundary methods lies in their ability to decouple the fluid dynamics from the complex geometry, thereby simplifying the numerical implementation. This decoupling enables the use of structured grids, reducing computational costs and improving scalability. The authors discuss the various formulations of immersed boundary methods, including the continuous forcing approach, the discrete forcing approach, and the cut cell method. The paper also reviews the application of immersed boundary methods to various confined fluid and plasma turbulence problems, including turbulent channel flow, turbulent pipe flow, and magnetohydrodynamic turbulence. The authors highlight the strengths and limitations of each method, emphasizing the need for further development and validation. Future research directions include the extension of immersed boundary methods to more complex geometries and the incorporation of advanced turbulence models. Overall, the review underscores the potential of immersed boundary methods to revolutionize the simulation of confined fluid and plasma turbulence in complex geometries.